Today we will begin looking at the product rule. To find the derivative of h of x equals x squared plus 2 times x plus 5 and k of x is equal to x plus 6 to the power of 3 times 2x minus 1 squared, what we would normally do is we would expand this first. However, this is very long and very tedious. So let's learn a new rule. So this rule here is called our product rule. If you're interested in looking at our proof, if you look at it on page 85 in your textbook, you can find it there. So if h of x is equal to f of x, g of x, then by our product rule, h prime of x is just going to be equal to our f prime of x, g of x, plus our f of x, g prime of x. So you're going to take the derivative of 1, multiply it by the original function, and add the derivative of the other multiplied by the original function. So let's just go ahead and start looking at a few examples. So we want to differentiate h of x equals x squared plus 2 times x plus 5 using our product rule. So we have our h prime of x is equal to, remember, we're first going to do the derivative of our f of x, which is x squared plus 2. So this is just going to be equal to 2x. Multiply it by our original g of x, x plus 5, plus have our original f of x, so x squared plus 2, times our derivative of our g of x, which is just going to be 1. And then from there what we can do is we can expand and simplify. So we have 2x squared plus 10x plus x squared plus 2. Collect our like terms, and we're left with 3x squared plus 10x plus 2. Now, if this looks confusing doing it all in one step, another way that you could do this is, look, say, my f of x I know is equal to x squared plus 2, so therefore that's 2 of x when we take our f prime of x. And we know our g of x is equal to x plus 5 when we take our g prime of x is equal to 1. And then you would have all 4 values that you need, and then you could just substitute it in to our product rule formula. So we'll continue with example 2. Again, we're going to differentiate our h of x equals x squared minus 3 of x times our x to the power of 5 plus 2 using our product rule. Now, I like to just do the derivatives as I'm going using my product rule formula, but again, as I showed you in the previous example, if you want to do your h of x, h prime of x, your f of x, f prime of x, and your g of x, g prime of x, please do so. So let's go ahead. So we have our h prime of x is going to be, we're going to differentiate our f of x first. So we have 2x minus 3. Multiply it by our g of x, so x to the power of 5 plus 2, plus our f of x, so our x squared minus 3x, and then multiply it by our derivative of g of x, which is just going to be 5x to the power of 4. We're going to now expand here, so we get 2x to the power of 6 plus 4x minus 3x to the power of 5 minus 6, and then we have plus 5x to the power of 6 minus 15x to the power of 5. Collect our like terms. So we have a 2x to the power of 6, a 5x to the power of 6, so we get 7x to the power of 6. We have a negative 3x to the power of 5, negative 15x to the power of 5, so we get negative 18x to the power of 5, plus 4x minus 6. And that is the derivative of h at x using our product rule. Now example 3, we're going to actually look at a value of x after we're finding our derivative. So we have our h of x equals 5x cubed plus 7x squared plus 3 all multiplied by 2x squared plus x plus 6. So again, we're going to use our product rule here first. So we have h prime of x. Take the derivative of our f at x first. So we get 15x squared plus 14x. Multiply it by our g of x. So 2x squared plus x plus 6. And then we're going to add our f at x, so our 5x cubed plus 7x squared plus 3. And multiply it by our derivative of g of x, or g prime of x, which is 4x plus 1. Now we could go ahead here and expand and simplify, but since we're actually just finding our derivative at a certain x value, which is -1, we can just go ahead and sub in -1 now for all the x's. So what we're going to do there, so we have h prime of -1, sub that in for all the x values. So bear with me here as I do that. It'd be even more time consuming and tedious if I expanded and simplified all this before subbing in our -1. And then, pardon me, hopefully you're able to fit it all on one line there. So then what we get is when we multiply this -1, this will be, that's -1 here, by squared, it would be +1, so we get 15, and then 15 minus 14, so you get 1. Here, -1 squared, so you get positive, where +1, so you get 2, 2 minus 1 plus 6, so you're going to get 7 plus -1 cubed here, so it's going to be -5 plus 7, because this -1 here squared will give it a positive, plus 3, so you're left with 5. And then 4 times -1 plus 1, we have -3. So we have 7 minus 15, which gives us -8. So h prime at -1 is equal to -8. So really what that's stating is the slope at -1 is -8. So now in example 4, we want to determine p prime of x if p of x is equal to f of x times g of x times h of x. So what we're actually going to do there is we're going to treat this f of x and g of x as m of x, because we don't know exactly how to do 3 functions when they're multiplied together and take the derivative of it. So we're just going to work with 2 functions at a time. So we're going to treat this f of x and g of x as our m of x, and as well, let's treat this h of x as q of x. So let's just first work with our m of x. So m of x is equal to f of x times g of x. So m prime of x would just be equal to our f of x times g of x plus f of x g prime of x. And that's just our product rule that we just learned. So now let's look at our p prime of x. So if we are looking at our p prime of x in terms of m of x and q of x, that is just going to be equal to our prime of m of x times q of x plus m of x times q prime of x. And we know from above that our m of x is just f of x and g of x, and our f prime of x is just using our product rule on the m of x. So using that, and our q of x is just actually our h of x, and we know that q prime of x is just going to be our h prime of x, because it's just one term we're talking about. So our m prime of x is equal to f prime of x, g of x, plus f at x, g prime of x, times our h of x. So again, this just comes from our product rule, plus now our f at x, because our m at x is just f at x times g of x, and our q prime of x is just h prime of x. Now we can expand this, so we get f prime of x, g of x times h of x, plus f at x, g prime of x, h of x, plus f at x, g at x times h prime of x. So what you'll notice here is that you're multiplying the 1 prime by 2 of the regular functions. And so you need to make sure that you're actually taking the derivative of all functions, f at x, g of x, and h of x. And what this is called the extended product rule, which makes sense, right? Okay, so now just talking about our product rule, what we need to do is we need to have a rule to solve something similar to the what's below here, our y equals x squared minus 3 all to the power of 4. Or what about y equals x squared plus 3x plus 5 all to the power of 6? So we do have a rule for that, and that rule is called the power of a function rule. So if f at x is equal to g of x all to the power of n, then our f prime of x is equal to n. So you're just bringing down the exponent, just when we were talking about our different rules yesterday. You're going to multiply it by our g of x. You're going to still subtract 1 from your exponent, and then you're going to take the derivative of your g prime of x. Now I did touch on this rule yesterday when doing one of our last questions, when we were just doing derivatives, and I told you we would discuss it further, so here we go. So using our new rule, the power of a function rule, in example 5 we want to find the derivative of each. So we're going to use that rule. So let's go ahead. So our y prime is just going to be equal to, bring that exponent of 4 down in front, so 4 times our x squared minus 3 all to the power of 4 minus 1. And now we want to multiply it by the derivative of our function x squared minus 3, which is just 2x. Now we can multiply that 2x by our 4 because they are just constants. So that's going to be equal to 8x times x squared minus 3 all to the power of 3. Similarly, in example B, our y prime, bring down our exponent, so bring down that 6, multiply it by our x squared, so our whole function, plus 3x plus 5. Our exponent's going to be subtracted by 1, so we have a power of 5, times what we have, our derivative of what's inside our brackets here, so times 2x plus 3. So what I'm going to do here is I'm going to multiply this 6 by what's inside our brackets here. So what we'll be left with is 12x plus 18 times x squared plus 3x plus 5 all to the power of 5. Now if you didn't multiply it in, that's quite alright. Both are the same answers here. So now let's look at example 6. Determine when the tangent of the curve h at x equals x minus 1 to the power of 10 times x plus 2 to the power of 5 is horizontal. So remember, anytime something is horizontal, our slope, so our m, is going to be equal to 0, always. That's not going to change ever. So because we are talking about our slope, we're talking about derivatives. We know when we're taking the derivative, that is our slope. So we are going to take the derivative of our h of x. So this will be equal to, we're first going to use our product rule, but we're also using the fact of we have exponents here. So we have a couple rules combined. So we're going to be using our product rule plus the power of a function rule all together. So we're first going to take the derivative of our f at x. So 10 times our x minus 1 all to the power of 9 times 1. Multiply it by our g of x. So that will just be x plus 2 all to the power of 5. Now, because it's product rule, we're going to add x minus 1 to the power of 10 times our g prime of x, which is 5 times x plus 2 times 1. Now we can go ahead here, and what we're going to do is we are going to actually factor out a few things that we can see that are similar in both sets here. So we notice when looking at this that you have an x minus 1 to the power of 9 and you have an x minus 1 to the power of 10. But just let me also mention the fact that we're not actually worried about multiplying it the 10 by 1 and the 5 by 1 because it's just going to actually be 10 and 5. I hope everyone can see that. So what we're going to do, we're going to factor out an x minus 9, or sorry, x minus 1 all to the power of 9, not minus 9 there, sorry about that. Also, when you're looking at your constants, I have a 10 and I have a 5. So with the 10 and 5, I know that I can factor out, so this is just common factoring, can factor out a 5. And then I also can see, looking at both sets here, I have an x plus 2 to the power of 5, oops, and I have an x plus 2 to the power of 4, there should have been a 4 written there before. So I can look at those two and I can see that I need to take out an x plus 2 to the power of 4. And when I factor that out, what I'm going to be left with, if you look in our first function here, I'm going to be left with a 2 times x plus 2, because I took out all my x minus 1's, and I'm left with 1x plus 2. And in the second here, I have plus, I'm left with an x minus 1. I can expand that, what's in our brackets over here. So I have 5 times x minus 1 to the power of 9 times x plus 2 to the power of 4. And when I expand and collect my like terms, I'm going to have a 2x plus x. So I have a 3x and a 4 minus 1, so a 3x plus 3. And then I can actually factor out a 3 from here, and when I do that, and when I factor it out, it's going to be 3 times 5, so I'll have 15 times x minus 1 to the power of 9 times x plus 2 to the power of 4 times x plus 1. And now, since I know the fact that my slope is going to be equal to 0 because of it being horizontal, I'm going to set that equal to 0. I have this in factored form already, so since it's in factored form, you can easily look at it and you can see what your x values will be. So we want to determine when the tangent of the curve is horizontal. So when that occurs is when, therefore, your x's are equal to positive and negative 1 and negative 2. So now in example 7, the position S in centimeters of an object moving in a straight line is given by S of t equals t times 6 minus 3t all to the power of 4, where t is greater than or equal to 0, where the time t is in seconds. So it makes sense that t needs to be greater than 0 because we're talking about time. So in part A, we want to determine its velocity at time t equals 2. So recall from Unit 1 when we were trying to find velocity. Velocity, we looked at taking the limit as h approaches 0. We now know that we can easily do this by just taking the derivative, a lot less steps. So I'm hoping everyone is starting to really enjoy derivatives. Determine its velocity at time t equals 2. First step is find our s prime at t, so our derivative. Again, we're going to have to use our product rule here. So we have this equal to 1 times our 6 minus 3t to the power of 4 plus t times 4 times 6 minus 3t all to the power of 3 times negative 3. Okay, and now what we can do, you can notice here, looking at this, we have a 6 minus 3t to the power of 4 and a 6 minus 3t to the power of 3. I can therefore factor out a 6 minus 3t to the power of 3. And what I'll be left with is a 6 minus 3t plus negative 12 all right, and now I have a 6, oh sorry, that should be a negative 12t, 6 minus 3t cubed. And we can collect our like terms. So we have 6 minus 15t. Now we want to find it when we have it equal to t equals 2. So since we know what our value is for t, we can now sub that value in. So s prime at t is going to be equal to 6 minus 3 times 2 all cubed times 6 minus 15 times 2. So what that's going to be is 0 times negative 24, which is equal to 0. So therefore, the velocity at t equals 2 seconds is 0 meters per second, or at rest. Now in part B, we want to determine the general velocity in simplified factored form. Well, guess what? We have already done all that work, and this is our factored form for our velocity. So we can just go ahead and write that down for B. So s prime of t is equal to our 6 minus 3t cubed times 6 minus 15t. So if you wanted to actually look at any position for t at any time, you can now look and say, I wonder what it is at 4 seconds. Put in 4 for your t value, you'll know what the velocity is.